Welcome back to the deep dive. Today we're setting the stage with something that feels honestly less like computer science and a bit more like a paranormal event.
Oh, yeah, definitely.
Imagine you were working late at night and you create a specific copy of your data to test a theory. You do this specifically to keep your original data safe.
Right, playing it safe.
Exactly.
Yeah.
And then you watch in real time as the original data changes anyway. It's like a ghost in the machine.
It's that terrifying moment where logic just seems to leave the building entirely. You change a variable over here and something completely unrelated just breaks over there.
I hate that feeling.
We all do. We're looking at a piece from the tech-reader blog today by a software engineer named Aaron Rose. It's titled The Secret Life of Python, the Copycat.
Great title.
Yeah, and it tackles one of the most notoriously tricky concepts in Python, which is memory management and the illusion of copying.
And what I really love about this article is that it wraps this very technical concept in a narrative. It's not just dry documentation. It's a mystery.
It really is.
We're following a developer named Timothy, who is in a pretty serious bind.
Right. Timothy isn't just, coding for fun on a weekend. He has a tight deadline. He's running the simulation for a chess club tournament.
High stakes.
Oh, absolutely. He's built what he calls the official bracket, which contains all the player pairings for the upcoming season.
And you really do not want to mess up the official bracket. Chess players take their rankings incredibly seriously.
Extremely seriously. So Timothy does what any responsible coder would do. He decides he needs a sandbox.
Makes sense.
Yeah, he wants to test some scenarios, like what happens if we swap a player here or there. But he is terrified of touching the master list.
Which is smart. That is just standard operating procedure. You don't run random experiments on production data.
Never.
You make a copy, you mess up the copy, and then you just delete it.
Precisely. So he creates a practice bracket. He thinks he's made a complete clone of the data to play around with. He makes a single change in his practice version, and then the blood just drains from his face.
The ghost appears.
The ghost appears. He prints out the lists, and the change he made in the safety of his practice bracket has somehow impossibly leaked into the official records.
Oh, man.
He's actually trembling. He tells his mentor, Margaret, "I've seen a ghost. The change followed me."
That is a total nightmare scenario. And our mission today is to exercise that ghost for you.
Let's do it.
We are going to unpack exactly why this happened, understand the actual mechanics of Python's memory, and figure out how to stop this copycat from ruining your data.
And to do that, we have to talk about envelopes, addresses, and the very misleading nature of the word copy in Python.
Okay, so let's analyze the crime scene here. What exactly was Timothy's setup? Because on the surface, his code looked perfectly correct.
It did the standard, yeah. He had a list called official bracket. Now, this is the crucial part. It wasn't just a simple list of names. It was a nested list.
Nested meaning lists inside of a list.
Right. Visualize the data structure. The main list represents the entire tournament, and inside that list, you have smaller lists representing individual matches. So the first item in the big list is a small list containing Alex and Alice. The second item is Bob and Barbara.
Okay, I'm with you. So it's a container that is holding other containers.
Exactly. Now, Timothy needs to make his copy, so he uses a very common Python technique called slicing.
Ah, the slice.
Yeah, you might recognize it as the square brackets with a colon inside.
Yeah, that's the standard way to clone a list. I mean, I've used that 100 times. Just type new list, o list, bracket, colon, bracket. It tells Python, give me everything from the start to the finish as a brand new object.
And that's exactly what Timothy thought. He creates practice bracket, official bracket slice. Then he goes into the first match of his new practice bracket and swaps Alex for his own name, Timothy.
Right.
He's thinking, great, I'm playing against Alice in the simulation.
But then he prints the official bracket.
And suddenly Alex is gone from the official bracket too. The official record now says Timothy is playing Alice.
Even though he explicitly only touched the variable named practice bracket.
Yes, and this is exactly where the panic sets in. He felt like the code defied the laws of physics. But then enters Margaret.
Ah, the senior developer mentor figure.
The best kind. Margaret walks in, sees Timothy shaking, and immediately diagnoses the problem. She tells him quite calmly, "It's not a ghost, Timothy. It's a shallow copy."
Shallow copy. It sounds super technical, but it's actually quite literal, isn't it? Margaret uses this fantastic analogy in the article involving envelopes to explain what went wrong.
She does, and it's brilliant.
Okay, walk me through the envelopes. I really want to visualize this for the listeners.
Sure. Imagine the official bracket, the main outer list. is a large envelope. Let's say it's a big yellow manila envelope.
Okay, big yellow envelope. I'm picturing it.
Inside that big envelope, there are smaller envelopes. Those are the inner lists, the individual matches.
Right.
One small white envelope has a piece of paper with Alex and Alice written on it. Another small envelope has Bob and Barbara.
So far, so good. Container holding containers.
Now, here is the trick. When Timothy used that slice syntax, Python did, in fact, create a new outer envelope for the practice bracket.
Okay, so he does have a new physical object. He has a brand new big yellow envelope in his hands.
He does, but, and this is where the ghost lives, Python did not create new inner envelopes.
So what on earth did it put inside the new yellow envelope?
It just took the addresses of the original small envelopes and wrote those addresses down inside the new big envelopes.
Oh.
Yeah. It essentially wrote a sticky note saying, for match 1, go look at that white envelope sitting over there on the official table.
Oh, wow. Okay, let me try to restate that to make sure I've got it.
Go for it.
I have my new practice envelope. I open it up, completely expecting to find brand new copies of the matches.
Yeah.
But instead, I just find references pointing back to the original matches.
Precisely. Both the official envelope and the practice envelope contain references to the exact same physical inner envelope sitting on the table. They are shared objects.
That's wild.
Margaret puts it a slightly different way. She says, there is only one house.
The one house concept.
Right. Imagine the data itself. The match between Alex and Alice is a physical house.
Okay.
The official list is just a piece of paper with the address of that house. When Timothy made his copy, he just photocopied the piece of paper with the address on it. He didn't build a new house.
So he has two pieces of paper, but they both guide him to the exact same front door.
Exactly. So when he follows the instructions in his practice envelope, he drives to that house, walks inside, and paints the living room wall. He changes Alex to Timothy.
And since there is literally only one house,
anyone who looks at the address from the official envelope and drives over there sees the exact same newly painted wall. The change didn't somehow follow him. He just went to a shared location and changed it for everyone.
that is just diabolical because the outer container really was different. If he had just added a brand new match to the practice list, that wouldn't have affected the official one, right?
Correct. That's a huge distinction to make. If he put a brand new white envelope into his big practice envelope, the official one wouldn't know anything about it.
Because the outer envelopes are separate.
Right. But because he reached inside an existing inner envelope, one that was shared, he caused the glitch.
This brings up a major point of confusion, though, which Timothy actually brings up in the article.
Yeah, he's frustrated.
He says, wait, isn't the slice method the standard way to do this? And he even references a previous incident, the author calls it episode 19, where they used the exact same method to fix a bug, and it worked perfectly.
This is exactly why this concept is so dangerous when you're learning Python. You learn a rule, it works great, and then suddenly it completely betrays you.
Right.
Margaret clarifies this beautifully. She explains that the slice acts as a copycat that stops halfway. It works perfectly for flat lists.
Flat lists meaning lists that just contain simple things like basic numbers or strings.
Exactly. This gets into the concept of mutability, which is just a fancy computer science word for changeability.
Okay.
If you have a list of numbers like 10, 20, 30, those numbers are what we call immutable primitives. You can't paint the wall of the number 10. It's just 10.
Right. If I want to change it to 11, I'm not physically modifying the 10. I'm just replacing it entirely with an 11.
Exactly. You're putting a new object into that slot in the envelope. So if you make a shallow copy of a flat list and you change a number, you are just swapping out the contents of your new envelope.
So you aren't touching this shared object.
Because you can't touch the inside of a number. It has no inside.
So the shallow copy is deep enough if the water is shallow.
I love that phrasing. Yes, exactly. If a list is shallow, just one layer deep, a shallow copy looks and acts like a full, complete copy.
But the copycat behavior emerges the second you nest data.
Yes. If you have a list inside a list or an object inside a list, the shallow copy only copies the outer container. It stops right at the threshold of the inner objects.
It's like it's too lazy to unpack the boxes. It just moves the boxes to a new truck, but they're the exact same boxes.
That's a great way to think about it. And that brings us to the pivotal moment in the story. Timothy is mildly traumatized at this point.
I would be too.
He asks Margaret, how do I get a real copy? I want to be able to burn the practice house down without singeing the official one.
He wants the nuclear option. Total separation.
And Margaret introduces him to the heavy artillery of the Python standard library, which is the copy module,
Huh.
specifically a function called copy.deepcopy.
Deep copy. It sounds like a submarine mission.
It acts like one. To use it, you just have to type import copy at the top of your script. Then, instead of using that slice syntax, Timothy changes his code to practice bracket copy.deepcopy official bracket.
And what makes this so different from the slice?
Margaret describes deep copy as an agent that is incredibly thorough. Unlike the shallow copy, which just glances at the inner items and jots down their addresses, deep copy travels down every single hallway. It opens every door.
So it's recursive.
It is recursive. That means if it finds a list inside a list, it doesn't just copy the address. It pauses and creates a brand new list.
Wow.
And if there's a list inside that list, it creates a new one of those too. It goes all the way down to the very bottom of the data structure.
So going back to the house analogy.
Deep copy looks at the original house, draws up the blueprints, goes to a completely different street across town, and builds an exact replica down to the furniture.
So now when Timothy goes to his practice house and paints the wall.
The official house is completely unaffected. It's on a different street. The ghost is officially gone.
That is such a relief.
It is.
When he runs the code with deep copy, he changes the name to Timothy. In the practice bracket, he prints the official bracket, and it still says Alex. Crisis averted.
Absolutely. The data is safe.
So this just seems like the magic bullet. Why wouldn't we just use deep copy for everything? Why even mess around with slices and shallow copies if they're potentially dangerous?
That is the exact question Timothy asks. It seems logical, right? If one is completely safe and one is risky, always use the safe one.
Right.
But Margaret gives a very important warning here. Depth has a cost.
Nothing is free in computing.
Never. Think about the analogy again, which is faster. Writing down the address of a house on a Post-it note, or building a full-scale replica of the house from scratch.
Writing the address takes 2 seconds. Building the house takes months.
Exactly. Deep copy is expensive. It takes significantly more processing time and way more computer memory.
I can imagine.
If you have a massive data set, say a list of 1 million transaction records, and each of those has nested details, and you try to deep copy the whole thing, you could slow your program to an absolute crawl.
Or just run out of RAM entirely and crash.
Right. You are literally doubling your memory usage for every deep copy. So it's a trade-off. Safety versus performance.
Yeah.
Margaret's advice is to use the right tool for the job.
So let's try to codify that advice. The source material essentially breaks this down into a cheat sheet that Margaret gives Timothy. I think we should run through this for you listeners to really cement it.
Sure, let's build the cheat sheet. There are 3 levels of copying in Python.
Level 1 is assignment. Just saying, BAA.
Right, and this is the trap. Assignment is never a copy. It is just a nickname.
A nickname.
Yeah, it's like putting a second name tag on the exact same person. If you touch B, you are touching A. There is only one object involved.
Okay, level 2, the shallow copy. This is using the slice or the .copy method.
This creates a new container. It is perfectly safe for flat lists of numbers or strings. But remember, it is highly dangerous for nested lists because those inner contents are shared. This is where Timothy got burned.
And finally, level 3, the deep copy, using copy.deepcopy.
This is the 100% independent clone. It separates everything. It's the safest option for complex, nested data. But you have to use it wisely because it's slow.
I feel like there's a missing piece here, though. Sometimes you're looking at code, maybe it's a legacy code you didn't even write, and you honestly don't know if you're looking at a ghost or not.
That's very true. Code can be pretty opaque.
And you can't physically see the envelopes inside the computer.
Yeah.
So did Margaret offer a way to check, a way to prove if 2 things are actually connected.
She did, actually. It's a great debugging pro tip involving the id function.
How does that work?
In Python, every single object has a unique ID number. It acts kind of like a social security number or a specific memory address for that object.
So how do we use that to find the ghost?
You compare the IDs of the inner items. So you would type id official bracket 0, id practice bracket 0.
So we're essentially asking Python, is the first match in the official list the exact same object in memory as the first match in the practice list?
Exactly. If that statement returns true, then the IDs match. The items are the same.
Which means?
You are in the one house scenario, and your data is not safe.
But if you had used deep copy,
then the IDs would be completely different. It would return false, proving that they are physically separate objects in the computer's memory.
that is such a handy tool to have in your back pocket. It just takes all the guesswork right out of it. You don't have to wait for your data to get corrupted. You can just check the IDs and know for an absolute fact.
It transforms the problem from a scary mystery into a simple fact check. And that is really the core lesson here.
Yeah, let's zoom out a bit. What's the big takeaway for you from this deep dive?
I think the author of the article put it best at the end. He wrote, "In Python, knowing what you are pointing at is half the battle."
Makes a lot of sense.
We often think of variables as boxes that hold things, like my variable x holds the number 5.
That's exactly how I was taught in my very first coding class.
Most people are. But in Python, that mental model is slightly wrong. Variables are much more like tags or labels that point to things.
Oh, I see.
The number 5 lives somewhere in memory, and x is just a tag pointing to it.
It totally changes your mental model of programming. You're not moving actual data around most of the time. You're just managing references.
Exactly. And when you finally internalize that, these ghosts stop being scary. They just become logic.
Right.
You realize, oh, I'm just pointing at the same address, and you fix it. It empowers you to control the machine rather than being confused by it.
And, of course, it saves you from the embarrassment of ruining the local chess club tournament.
Which is arguably the most important part of all this. You really don't want a bunch of angry chess players coming after you. They think several moves ahead.
Absolutely. Well, this has been a really fascinating look under the hood of Python's memory management. It's one of those things that seems so small until it bites you, and then you just never forget it.
And speaking of things that bite you when you least expect it, the source material actually leaves us with a little teaser for the next adventure of Margaret and Timothy.
Oh, really? What is it?
It's called the default trap.
Ooh, that sounds ominous.
It hints that giving a function a default list, when you define a function and put an empty list as a parameter, is like, quote, sharing a toothbrush with a stranger.
Sharing a toothbrush?
Yeah.
That is disgusting.
It implies that the default list is created exactly once and then shared across every single call to that function forever.
Oh, wow.
Yeah, it's another reference trap just waiting to happen. So, something for you to ponder before we meet again.
That sounds like an absolute disaster waiting to happen. I cannot wait to unpack that one. Thank you all so much for listening to this deep dive into the secret life of Python. Keep your references straight, watch out for those ghosts, and always check your IDs.
Happy coding!